Hi everybody, thank you for joining me. My name is Solomon. Before we start, I just want to say that this presentation will feature a lot of source code, and the goal of this presentation is not to hammer you with source code and make you understand every single line of code. The goal of this presentation is to outline for you all the steps and the process that you have to take in order to use C and native platforms in Kotlin. Second information, this entire presentation is written in Kotlin Multi-platform with Compose Desktop. So what you are seeing is a Compose application. It also runs on the web, but as you may know, it will not run on Safari or neither will it run on iOS. So if you want to see the slides either on your Android device or on your Chrome or any other not Safari browser, you can go to this link, p.codein.net/KC24, and of course you can see the slides after this presentation. But it will not work neither on Safari nor on iOS for the time being. So, you want to use native APIs in Kotlin multi-platform projects, do you? You fools. For this presentation, I'm going to try and make SHA-256, SecP256K1, and ChaChaPoly work in Kotlin multi-platform. So these are three crypto primitives that are used in the cryptography world. SHA-256 is a hashing function that's very known and very used. SecP256K1 is a cryptographic primitive that is used, for example, by Bitcoin. This is not an endorsement of Bitcoin. I don't want to state any opinion on Bitcoins, but, you know, SecP256K1 has been heavily audited by people who, you know, want to get rich. So why not use it in other circumstances? And ChaChaPoly is a modern cryptographic API. We're going to target all these platforms. So by JVM star, I mean JVM and Android, because Android is very close to the JVM. We're going to, of course, target all Apple devices. We're going to target Windows via MinGW, Linux, and, of course, WASM and JS. These are the platforms that we are not going to be talking about, and I'm not going to target it in my samples. I'm not going to target Android native because, you know, who targets Android native with Kotlin multi-platform? It's very, very niche. And I'm not going to target Linux ARM64 because at the moment you can compile for Linux ARM64, but not in a Linux ARM64. You need to compile for Linux ARM64 from an x64 Linux. There's no way to run the Kotlin native compiler on Linux ARM64, which makes testing very complicated. You know, you need to compile on Linux x64 and then run the test executable on ARM64. That's not a great experience, so let's not talk about that. So the main problem when you're using Kotlin C API in Kotlin multi-platform is that there's no standard way of doing it. And let's take our example. We have some platform API provided by Java. So that's easy. We all know how to use Java API in Kotlin. We have C APIs that are provided by the Apple system or the Windows system. And hooray, we can use C APIs directly in Kotlin. We have JS API that are provided by an external library. I'll use an NPM dependency. We have a C external API, so SecP256K1 is only provided as a C library that's been provided, that's been heavily audited, but we need to port it, we need to import it into the JVM. For that, we need JNI. For Kotlin native, we need the Kotlin native generated facade via C-interop. For the web, we will compile it to WASM, so it's yet another API. And ChaChaPoly, for example, which is a very modern API, it's only provided by Apple in Swift and by Windows in C#. So how do we import that into our Kotlin code? And finally, how do you import ChaChaPoly in the web? I don't have the solution. The only solution I found is to compile the entire OpenSSL library to WASM. because I don't trust a random NPM package with a very important cryptography primitive, so yeah, you'll need to figure it out. So this is the entire table of every single target and every library, and as you can see, each entry requires a different treatment. So let's start. Let's say that I have a need for a SHA-256 common facade, and I want to implement that in each of our targets. Well, the JVM is simple, right? Not much to it. You just forward the API to the Java API. Simple, right? Well, turns out that commonization is not supported for JVM and Android. So if you're writing a library that will target each of your each target, including JVM and Android, and will target both JVM and Android and have some features that differ, then over the 3 years ago, this issue was opened, and at the moment, it's not resolved. So that means that, well, you take your SHA-256 JVM implementation, you copy-paste it, and you have the Android implementation. That's bad. So I don't want to duplicate my JVM and Android code, so what other choice do I have? Well, I could extract the shared code that is JVM only into another library and have my JVM and Android targets for my main library depend on this library. So with this solution, I have another library that only contains the JVM portion of my library, JVM portion that is common to both JVM and Android. Or, you know, I could try to detect JVM in the bytecode and run in different paths. But of course, if you need a context, then it doesn't work. So how do you commonize JVM and Android? Well, that's the first problem you're gonna have. Okay, you've defined that, and now let's talk about using C API in Kotlin native. So here's the example of how you would do that with the Apple API, and with Kotlin native, you can access C constants, you can allocate and free memory on the native heap memory stack, and you can also simply call C functions. So here, for example, I access the native memory that's underlying my byte array, and I pass that as a pointer to C functions. And for that to work, you don't have anything to do, because Kotlin native comes with pre-packed all Apple APIs in all Apple C and Objective-C API for, in Kotlin native for iOS, and all C and Objective-C and C API for Windows in Windows. So as you can see, you can directly call the functions. For Windows, it's the same, only because it's Windows, it's more complicated. So, for example, this is how you get the length of the digest. You need to call this b create get property, pass it DW flags and all these parameters, but basically, it's just calling C functions, which we've seen is easy. The only item of interest in this code is that memscope. Memscope allow you to allocate memory that will be automatically freed when you exit the scope, so no more native heap.alloc and no native heap.free. It's an easier way to ensure that you don't have memory leaks. Okay, so these are APIs that are provided by the system and imported into Kotlin native for you. How do you do that with a Kotlin native C API, so a library that isn't provided by Kotlin native? So, for example, I want to use the SHA-256 features of OpenSSL. So that's an external library. And before discussing how we will implement SHA-256, let's talk about external libraries in general. And the first question you need to ask yourself when you're going to import a native external C library into your Kotlin native application is, do you use static or dynamic libraries? So it helps to understand at a very higher level what's the difference between a static library and a dynamic library. A static library is just a table. It's binary code that's been compiled, but it isn't executable. It's a list of symbols, meaning constants and functions, that are provided by these tables, but because it hasn't been linked yet, it's not executable. It has a table of defined symbols inside this library, but it also has a list of symbols that it doesn't define and that it will need in order to become executable code. So if you have such a table, you could have multiple objects, compiled table, and when you link them, you get an executable. An executable is the same thing except that it doesn't have external symbols. Everything it needs to run is inside the executable. Yes, I know this is a very higher abstraction. It's not entirely true, but it's sufficient to understand the difference between static and dynamic. And so an executable is a list of symbols that are linked together with a main function so that you can start the executable. And what's interesting to know is that an executable can, at runtime, access other executable binary libraries. So these are tables that contains executable code, but do not provide the main function. So the difference between an executable and a dynamic library is just it doesn't have a main function, but it's executable code that has been linked. And that's the main difference between static or dynamic. So static libraries are linked with the application and included in the klib. So they're included with your library. Whereas dynamic libraries are accessed at runtime, they are provided by the system, and they may be reused. For example, there's only one OpenSSL in your Linux distribution because there's no need to embed OpenSSL in every executable that uses it because it's a big library and it can be reused between executables. So now that I've understand that, I want to use Kotlin, this Kotlin native C API with an external OpenSSL dynamic library, because I'm going to assume that if you're running this on Linux, then you have OpenSSL installed, because who doesn't, right? Right? Well, the Linux ecosystem is, of course, known for its library ABI consistency across all distributions, right? Of course not. So as soon as you're using a dynamic library, you need to assert that. You trust Linux distribution to provide OpenSSL. You trust OpenSSL backward compatibility application binary interface, because if OpenSSL updates and breaks its ABI, then it won't work. You will only use OpenSSL 1.1 because, you know, for example, Ubuntu comes with OpenSSL 3, but Alpine comes with 1.2, so who knows which OpenSSL version you'll have, and you need to trust anti-corruption system policies, you know. If someone manages to corrupt the OpenSSL dynamic library of your system, then you're in deep that. So you can also use a Docker container and it makes your life a lot easier. Okay, so now that I've decided all that, I write my Kotlin native C-interop definition file. So, how does it work? You write this definition file, you put it inside the C-interop, SRC native interop, C-interop folder, and what does it say? Well, it will generate some code for you. So that code will be in this package. It will generate some code from that header. So you give it the header, but a header includes all other headers, which includes other headers. So you need to tell it, okay, generate some code only for headers that are inside this folder. I don't need you to generate code for headers that are, that's stdio.h, for example, or system headers. I just want the code that corresponds to the headers inside OpenSSL. And then you need to give it some compiler options, namely where to find the headers. And finally, you need to say, okay, when you link with crypto. Now, what's interesting is to know that klibs are static libraries. So when you build your klib, it will not link this this -L crypto will only be passed to the linker when the application is linked. So it will be part of your klib, and when application uses your dependency and your klib, inside the klib it will be marked, okay, when you link me, you'll need that library for that. Okay, so once you've done that, you need to tell Gradle that you have a definition file, a C-interop, and then you can write your C-interop function. And that's very easy. It's the same. Once you've done the def file and told Gradle that there's a C-interop, it's very easy. You see, I can call this function, I can call this function, I can call all these functions just like I was using Platform API, because actually, Platform APIs are integrated into Kotlin Native using this C-interop system. I just need to remember that I'm handling native memory, so I need to, of course, clean after myself. Okay, I've written SHA-256 for JVM, Android, and all Linux systems and iOS systems, and I'm ready. Let's try. Well, I run Gradle check, and there's no header, because I'm on my Mac, and on my Mac, it's not the same header locations, so I need to provide it the headers, okay? I do that, and it still doesn't work. It wants to link with crypto, but I don't have crypto, because crypto is for Linux. On my Mac, I use the Apple C libraries. So, what do? Well, turns out cross-compilation is enabled by default, and there's no API to configure or disable it. And if you're going to link with a Linux dynamic library, then suddenly cross-compilation will not work anymore, and it will be very complicated to make it work. Yeah, this issue has been there for 5 years, and there's still no proper API to disable cross-compilation. It's kind of infuriating. There's a workaround. You need to put all that into your Gradle and trust that it works, and it works. But it's suboptimal. You need to config to comment it and say, okay, this disabled cross-compilation, because there's no other way. Let's hope one day JetBrains addresses this issue. Okay, so now we've done SHA-256. Let's move on to SecP. So SecP is a C library, as I've said, that's available on GitHub. It's been heavily audited, so we can trust in it. So let's use it as a static library this time. It's not a library that's provided by the system. It's a static library that we will embed into our klib. So, of course, what now? Are you ready to compile for 18 targets spanning over 7 different operating systems with 5 different tool chains? That's the pain of using static C libraries for Kotlin Native. Namely, you need to compile for all these targets. And that's a compilation process that's different for each operating system and each tool chain. Here are some examples. You want to use auto tools, which means, you know, configure, make, like we're in the 80s. How do you do that on Apple targets? Well, on Apple targets with auto tools, you define a bunch of external variables, of system variables that define where is the C compiler, what are the flags, where's the sys route to compile to, what's the host, etc., etc. And then you run configure, you run make, and hopefully you have a compiled C library. And you do that for each Apple target. For Android target, it's the same. It's not exactly the same system variable, but it's the same. You define where to find the compiler, the linker, all binaries that are used by the C compiler and the toolchain, the AutoTools toolchain to compile. And for desktop and server targets, at least it's simple, right? The library provides everything, because most of libraries you can just configure and make and it will run for your machine, right? Right? Well, it turns out that Linux Kotlin Native is linked against a custom sysroute because every Linux is different. and you want Kotlin native for Linux to run on each Linux. So instead of compiling with your system, it will compile with a sysroot that is provided by Kotlin native. So you shouldn't compile your library with your host toolchain. You need to compile the static library with the Kotlin native toolchain. Which means that actually it's simple for Windows and Mac, but for Linux, you also need to override a set of system variables. These are always the same, the CC, the LD flags, the LD binaries, etc. and etc. Okay, so that is if you're using AutoTools. What if you're using CMake to compile your library? Well, for Apple device targets, there's a project on GitHub called iOS CMake that provides you with a toolchain CMake file that will very simply allow you to compile any library with, or most libraries, let's not overpromise here, most libraries for all iOS targets, all Apple targets that you want to compile to. And let me say a huge thanks to its maintainer, because this project has saved my life. For Android target, there's also a toolchain CMake file that is provided directly by the Android project, so thank you, Google. You'll find it in the NDK folder of your Android SDK, and it works the same. For Windows and Mac, it's simple, just run CMake. And for Linux, you need to override some system variable to tell it, okay, let's not use this system clang, let's use the Kotlin native C compiler, let's use its sysroot. Okay, that's for CMake. So we've seen AutoTools, we've seen CMake. What about, Bazel, Ninja, Scon, Stop? There's a lot of ways to compile for C and C++ codes out there. How do you do? Well, my answer is, why are you bothering me? Figure it out by yourself. Each library is different. Each system library is different. What, you want to take a picture? There. Okay. So just figure it out, because each library is different and there's no easy answer. So you have compiled the C library for all the targets you want. You have C libraries for all iOS targets, all Android targets, all Linux, all everything. So now you write the dev file. And this dev file is great, it's simple. Okay, here are the headers. Here's the static library. So this is very important. It says, okay, you will embed this static library in the klib. And then you're very proud of yourself, and then IntelliJ tells you you're incorrect. But it compiles, it works. So, C-interop definition tooling has not been updated since its creation, and it is not aware of newer targets. And JetBrains should be aware of that for at least 2 years. And this is the one that angers me the most, how hard it is to update your tooling and have it at least compatible with the code that you are providing. So this is correct, but IntelliJ will tell you that it is not. So please vote for this issue. It has bugged me in my sleep. Okay, and finally, you can write the C code. And I'm not going to go over that again. It's just using C code inside Kotlin Native. You're getting used to that. And that's for Kotlin Native. And that's pretty easy-ish. Compile, write the dev file, use the C code. Okay, what about the JVM and Android? There's no C-interop for JVM and Android. So you need to write a JNI facade. So first of all, you need to write a bunch of external function, a class containing a bunch of external function, and yes, there's no better way to handle pointers than to convert them to long, because in C a pointer is basically a long, so there's no pointer type, so we use long. Then you need to write a C facade in C, and that's the pain. You need to write, you need to understand C, and you need to write this facade in C. For each external function that you have defined, you need to write the corresponding C function using the JNI C API. And then once you've done that, you need to compile your JNI C API, which is, you know, another journey on its own. So to me, the easiest way is to use CMake, because with CMake you can actually say, okay, find me the JNI headers and link the library with the JNI. What's interesting is here, this is a shared library. So even though you're using a static library, you need to compile a dynamic library with your C shared with your C static library and your C facade, your JNI facade that corresponds to your external Kotlin or Java function. Once you've done that, you need to tell Gradle, hey, I've done a CMake, integrate that into the build chain, and that works. For Android, it's easy, but there's no such way to do that for the JVM or Android, which means that you need to write your own task, your own Gradle task, and register your task, and run CMake as an external tool, and copy the output, the resulting dynamic library into your resources, and all that, because it's not provided for you. And then in Kotlin, you need to load your library. So for Android, it's simple. The library is inside the AAR. You call system.load_library, you're done. Cool. But for the JVM, you need to find the dynamic lib extension for your current OS, because, you know, on Windows, it's DLL. On Linux, it's SO. On Mac, it's dlib. Why? You need to create a temporary folder, extract the library to it, load the extracted library with the correct path and extension, or you can use this project, which does exactly what I've just said for you. But if you have a custom loading business logic, then you'll need to do it by yourself. And then finally, you can write the facade using your JNI function. So here, it's a very simple code, and I use this secp256k1.createContext function that delegates to JNI, that then call the corresponding function to the C library secp256k1. Okay, so the JNI process is this one. You need to compile a native lib as a static lib, write a JNI wrapper is C, compile the JNI wrapper and your native lib, link them as a dynamic library, write a Kotlin JNI facade, and then write implementation using that facade. Maybe you've heard about JNA. JNA is a shortcut to JNI. I'm not going to go into details about JNA, but basically you compile the lib directly as a dynamic lib, and then you can load it and access its symbol. But there's two problems. The first problem is because there's no generator for Kotlin code using JNI. There is for Java, but there's no such thing for Kotlin. You're going to have a lot of trial and error in order to understand what are the correct definition, the definition in Kotlin, and you have some performance loss. But it's easier, so it's up to you to choose which one you'll use. Here's an idea, though. You know what would be cool? What will be cool is a unified C-interop that would work across all targets. So I'd love to have C-interop that works both for Kotlin native and for the JVM. And you know what? Back in the days, there was a prototype to do that. JetBrains actually tried that, and they laughed and decided no. So there's an issue. What I know now is that it's not going to happen anytime soon. It would be amazing. There are some projects that try to do that, but it's not really C-interop. But yeah, that would be amazing. And my message to JetBrains, please reconsider your position, because C-interop is much more helpful than JNI, which is known to be a pain. Okay, let's dive into our third library. Chachapoli is a known cryptography primitive that is provided by systems, and by systems I mean Apple and Windows, because Linux, doesn't provide anything on its own. It's all inside libraries. But Apple only provides it as a Swift API. And we know that at the moment, Kotlin only interrupts with Objective-C. It will change one day. But right now, we are left with having to interrupt with Swift via Objective-C. Okay? So you've seen a lot about how to write Kotlin code that is usable in Swift and all the tips and tricks that you can use in order to use Kotlin code in Swift. Let's go the other way around and see how we can use Swift code in Kotlin. So, the first thing you need to do is write a Swift static library with an Objective-C bridging header. So what that means is that you're going to access the platform API in Swift, but provide a way to access this same API in Objective-C. So it's up to you to write the bridge between Swift and Objective-C. And in this code, the only feature of interest is that at Obj-C before the public class. It basically says, okay, this class will be accessible to Objective-C, and if it has stuff that isn't compatible with Objective-C, then don't compile. And it returns a class that you need to trust me, I've written, and is also Objective-C compatible. So I create a Swift facade that exports an API that is readable by Objective-C. Once I've got that, I have an Objective-C-like header, and I can import it into Kotlin Multi-platform. So what do? I create a dev file for every C-interop, and what's new here is this language equals Objective-C, because, well, by default, C-interop is for C, but C-interop also happen to understand Objective-C, so if you're reading an Objective-C header, you need to tell it, this is Objective-C, not C. But the rest is the same. Those linker-ops are a bit different too, and the main reason they're needed, the iOS simulator version min, by default, Kotlin native will generate binaries that are compatible with iOS minimum version 9. But as it happens, the Swift ABI that is provided by Xcode is compatible with iOS minimum version 13. So you need to change the default minimum version that this klib will be compiled to. And then once you've done that, well, you can use Objective-C API just like you would in Kotlin native, just like we've covered many times before. The only new thing here is because we're using Objective-C and not C, we can access the auto-release pool, which is another way of auto-managing the memory and making sure that we don't have memory leaks, native memory leaks. And what's also cool is that because we're using Objective-C and Apple libraries, well, we could have things like, okay, I want to access the native memory of my byte array, so I pin it, but I don't know when will I need to unpin it, and I can give a deallocator when I create the NS data. For example, I can say to Apple when this NS data is reclaimed, then you can unpin the memory. So you can, have some little tips and tricks here and integrate yourself into the native memory Objective-C handling. I've written an entire blog post in order to do that. I've not told you everything because there are some weird bugs and tips and tricks you need to know. If you want to integrate Swift API into Kotlin native and Kotlin multi-platform, I encourage you to read these blog posts. So this is basically how it works. We have Swift API rewrites a static Objective-C facade that accesses this Swift API, and then I can integrate it into my Kotlin native. And basically, it's the same with Rust, for example. I'm not going to show you Rust, but take any language that is capable of building a static library with a C header, and you can integrate that into Kotlin native with the exact same process I've shown you. What about Windows? Well, the problem is C# doesn't run on its own. It's not native binary code. It uses CLR, which is basically the same as the JVM. So what you need to do is to write a static C facade that will access the DLL. You need to write a C# dynamic library and write a C facade that will access the DLL and access the function. And there are several ways to do that. You could host a CLR runtime into your static C facade. You could use Windows COM messaging in order to dialogue with C#. It's up to you. I haven't done it. I pray I will never have to, but that's how you would do it if you would absolutely need to do it. So I've told a lot. I've talked a lot about native and JVM, but what about JS, right? We wanted also to target JS. Well, for an npm JS library such as SHA-256, we can trust it because, you know, SHA-256, it's easy to verify the algorithm. So let's add an npm dependency, and then let's declare our module. Once we've declared our module, so basically we're saying, we're telling to Kotlin JS and Kotlin WASM, by the way, it works exactly the same, that these are the functions that are provided by my function. Then I can write, then I need to write some utilities to transform byte arrays into int8 arrays, you know, data buffers for JavaScript. And by the way, these utilities I've used everywhere. And just saying, this issue asking for it to be provided in the standard library has been open for more than 5 years ago. Just saying, but you need them. And then you can write your JS library using your external module, easy. How about WASM, a C library? For example, SecP256K1 is a C function, is a C library. How do you use it? Well, Kotlin WASM uses WASM, and mscriptm compiles to WASM. How about linking, you know, and yeah, of course not. There's no C-interop for Kotlin WASM, and no way to link with an external library. Yet, give JetBrains some slack, Kotlin WASM is in alpha. So it was experimental, now it's in alpha. So it's probably coming just at the moment. What we need to do is write a C facade with this mscriptm keep alive. So what it will say is that this function will be exported to JavaScript and it will stay alive inside the WASM binary that will be compiled by mscriptm. And then we compile it. So this is, for example, how I compiled this SecP256K1 library. I use the mscriptm C compiler. I give it some sources, so namely the SecP256K1 sources and my facade with my mscriptm keep alive annotated functions. I give it some output. I tell him to emit some TypeScript definition just because I want to know what's been generated. I will not use it in my program, but it helps me to understand what's been generated. And I also need to tell it, okay, it's for the web. You need to modularize it so I can import it as a module. And because I'm also going to allocate memory, I need the malloc and free functions. Once you've done that, it generates this TypeScript definition. The most important thing is, yeah, you have access to the free malloc and the function that I've created in my facade. Once I've got that, I can write Kotlin. I define the module. In the module, I define what's defined by the module, and then I can use the module. Oh, sorry. And then I need to write the uint8 utilities that are requested, and then finally, I can use the module. What's interesting here is how you handle memory. So you can use malloc, which returns you a pointer, and then you can access the WASM memory using this weird heap U8 stuff. Now, what you need to understand is that there will be two WASM runtime running at the same time, and that's the shame of this method. There's your WASM runtime, the WASM runtime that executes your application, and because you compiled your C library as a different WASM executable, it runs in a different WASM runtime. So you will have some performance loss, and you will need to copy-paste some memory from both WASM runtime, which is not ideal, but it's the only solution we have. So then, once we've allocated memory, we can use that memory, call the function with those pointer, and of course, let's not forget to free the memory behind ourselves. So that's how you handle native C libraries inside WASM. Basically, you compile it to another WASM binary. So if you have multiple libraries, I encourage you to link them all together in order to have only 2 WASM runtimes and not 1 WASM runtime for each of your libraries, which will probably make your browser mad. So let's recap. If you want to use native APIs in Kotlin Multi-platform, you need to understand C and Obj-C. You need to understand Kotlin C-interop and how it works and the API it provides you. You need to understand JNI or JNA. You need to understand system compilation configuration, how sysroots function, how you can configure your toolchains. You need to understand native toolchains, how they work, how you can configure them. You need to understand modern languages if you are going to use the API they expose. You need to understand how WASM manipulates and exposes memory. It is an amazing journey, and I do encourage you to try it out because you will learn so much about computing in general and how it works. I just hope that one day it becomes less of an amazing journey in the future because, let's be honest, there's a huge barrier of entry, and it could be lowered. So, that's it for me. I just require 30 seconds of your time for the corporate stuff. I represent Coding Coders, a company that's heavily invested in Kotlin Multi-platform. We are certified Kotlin trainers, so if you need to understand Kotlin native, Kotlin Multi-platform a bit more, don't hesitate to call us. We also provide consulting and development services, and we also have an open source initiative where we provide open source libraries for all targets that Kotlin can provide. And in fact, this entire library, this entire presentation is written with a framework for Compose Multi-platform that you can try now. Thank you very much. Don't forget to vote, but of course only if you liked this session. You have, once again, the link to the slides, and I repeat, it won't work on Safari or on iOS at the moment. If you want to know how this presentation was made, you also have the link of the framework that we've written specifically for this. Thank you very much. I don't think we have time for questions, but I'll be around.